All right, let's kind of keep going with pumps here. Let's try and take care of a couple of things. A couple other calculations we can do with these. First one is called NPSH. Now this is something that really only applies if you're lifting water out of a reservoir. And yesterday, or last time, we were looking at a video that showed a pump cavitating. This relates to that deal where pumps start to cavitate. And I think I posted links to those videos in Moodle, I think, if you care to have a look. Okay, so this is N is for net, P for positive, S for suction, and H for head. So what we're doing here, we're looking at the energy in the volute, okay? So in the pump, there has to be a certain amount of energy, and the NPSH is the measurement of that energy, is what it is. I'm on page 141, is where I'm at. All right, so page 141. Now, pumps that have static head, generally speaking, have enough NPSH because the water is flowing by gravity into the pump, into the volute. So they're not the problem. The problem is when you lift water out of a reservoir. That's when you kind of have to check this, all right? So you use it when you've got what's called the static lift condition, where you're lifting water out of a reservoir. When you do that, you might not have enough energy in the water when it's in the pump, in the volute, okay? So to figure out how much energy you've got, what you do is you take the amount of energy you start with. Now, let's kind of remember how this is working when you pump water. When you pump water, you start to spin the impeller, and what that does is that throws all the air out of the volute. That's the idea. So right at the center of the volute, you've got a vacuum. Okay, that's the idea. Sorry if I'm rolling through all this stuff here. I didn't realize I had so much stuff, but let's, there we go, right there. See, when that impeller starts to spin, it throws the air out from the center of the impeller, and what it leaves behind is a vacuum. All right, so that's the idea. So there, right in there, when you start spinning that impeller, you get a vacuum right in this area. Okay? All right, so what you have then, if you have a pump then where you're lifting the water, is now you've got the atmospheric pressure pushing on the inlet reservoir. All right, so that's what's happening there. So when you create a vacuum in the pump, what you have is atmospheric pressure that's pushing down on this reservoir, and it pushes the water up the pipe into that empty space that has no pressure because there's a vacuum there. That's the idea. Okay. Now, how many feet is atmospheric pressure? You all remember that?
14.3?
That's PSI, 14.7 PSI, 34 feet. Okay? That's what atmospheric pressure is. Okay? So if that's a perfect vacuum in the pump, which honestly it's not, but if it were, you could lift water 34 feet. That's it. That's the maximum. But you've got some things that make it a little bit difficult to do that, okay? So you start with your 34 feet, and that's at sea level, kind of an average pressure at sea level. But then you've got to subtract off a few things to figure out how much energy you've got. Okay, the first thing you got to subtract off is how high you're lifting the water, right? So if you got 34 feet of atmospheric pressure at that reservoir and you're going to lift the water 10 feet, you got 24 feet left, right? That's how much energy you're going to have. So that's one thing you subtract off. But there's a couple other things you got to subtract off too. One thing is the head loss. So if you have fittings and a certain diameter of pipe and all that, you got to figure out how much head loss you got as you're pushing the water into that pump. Okay? And the water's going to lose energy when it rubs against the pipe walls and goes through the fittings and all that. So that's going to take energy away. Okay, so you got to lift the water. You got head loss as you lift the water. But there's one other thing that goes on here, and that is that you don't have a perfect vacuum in the pump. Even though it's throwing the air out, there's a certain temperature that's going to evaporate some of that water. So that isn't a perfect vacuum in the pump. It's a partial vacuum. All right. And what's going to push back is something called the vapor pressure, which I don't know if you remember when we went over this briefly, but we did. And there's a table that will tell us what that vapor pressure is. Okay, and that's back in chapter 1, page 58. So if we have 73-degree water, or 70-degree water on page 58, we're going to have a vapor pressure, which is kind of the pressure of the water molecules that are evaporated, of 0.8 feet. Okay? So that's going to push back too. That's on page 58 for 70-degree water. All right? So if we want to know how much energy there's going to be in the water when it hits that pump there, we start off with how much we've got to start with, which is the atmospheric pressure in feet, which if I don't know any better, I'll call 34 feet, okay? So I'll start with that, and then I'm going to take away the vapor pressure, I'm going to take away the lift, and I'm going to take away the head loss. And that'll get me how much energy I've got left over in the pump. That's how that works. Okay? So what I'm going to do then is I'm going to figure out this stuff for my conditions. So I got 34 feet. That's what I start with. On average at sea level, that's the pressure. But the vapor pressure is 0.8 feet. I got to subtract that because that's pushing back against the water as it's being lifted. Well, how much static lift do I got on this one? To get into the pump now. Oh. See, I'm not looking at the full lift. I'm looking at what it takes to get the water into the volute.
6 feet?
Yeah, 7 feet. Yeah, okay. Now what 7 feet is 501, which is where that volute's at, the pump's at, minus where the water's starting, which is 494. See, that's 7 feet. So the first two numbers are pretty easy to get. It's head loss is going to take a little bit of work, okay? Okay, now the suction side piping length, what do I got for that?
Do we just assume that it is 70 degrees?
It's given there, I think. Or maybe,
Yeah, it's 142? Right, 142, yeah.
Yeah, okay.
70 degrees.
So I'll put that in there. Good for me. I don't even see it anymore. Yeah, so yeah, you should know the temperature. But you could assume roughly what it's going to be, if you weren't given it. Okay. All right. Now we have the suction side piping length, and that's 12 feet, right? That's given. So we're going to do the same sort of thing we did before, but now we're going to do it for just the suction side, just the piping going into the pump. So that's 12 feet of pipe coming in. Okay. We've got a standard elbow, and that's got an L over D equal to
28?
Yeah.
Standard elbow is
664. The other one's 28. And then the extended outlet, right?
Wait, on the suction side? Oh,
Yeah.
okay, sorry. I was
Yeah, you're looking
at the wrong one, sorry.
Yeah, right. And so it's 28 for the one you were calling out, right? The whatever that was, the elbow.
Extended outlet.
Yeah, extended outlet. Yeah, okay. All right. So now we're doing the minor losses. So we can come up with a total. And the total is what? Is that 92? Okay. Is this 8-inch pipe?
Yep.
Okay, so 8-inch pipe. A foot to 12 inches is 0.667 feet. Okay. So what we're going to do then is we're going to take that 92 feet of pipe, that's L over D, and we're going to multiply it by D, which is 0.667 feet. And that's 61.33 feet. Okay, so what that means is those fittings have the same head loss as 61.33 feet of pipe. Y'all okay with that? Okay. Now our head loss per 100 is 4.85 feet. That's just on that head loss chart on page 108. Okay. So what we can do now is we can take the pipe length, which is 12 feet, and add it to our equivalent length of the fittings. And one piece of advice they give you is to minimize the fitting length on the suction side because of this effect here. See, we only got 12 feet of pipe, but all those fittings, when we put those in there, we get quite a bit more length of pipe, equivalent length of pipe we're going to have to figure out head loss for. Those fittings get us from 12 up to 73.33 feet, okay? So I got 73.33 feet of equivalent length of pipe. That's the pipe plus the fittings, okay? And for that size of pipe and the flow, if you look on page 108, we'll get 4.85 feet per 100 feet. So we can get the head loss then. It's 3.56. I didn't have room to put that at the bottom. I don't know, maybe I could have. Maybe I'll do that just to get a little bit more organized here. So that's 3.56, okay? So that's the head loss. That's what happens when the water runs through 12 feet of pipe and also 61.33 equivalent feet of fittings, okay? That's the result of that. So that's energy that's being burned up as the water moves through that piping. All right, so we start off with 34 feet of atmospheric pressure. We got 0.8 feet of vapor pressure pushing back. We got to lift the water 7 feet, and we burn up 3.56 feet of head loss just doing all that. So what we end up with then is 22.64 feet of energy in the volute. Okay, so that's what we got left over. So what they, though, if you learn a little bit about this, if you're having cavitation problems with your pump, which is caused by not enough energy in the volute, the general advice on what to do on that is to lower your pump, which reduces that static lift. And it's also to minimize the number of fittings you've got in that piping. You don't want to be stacking a bunch of valves and stuff on the suction side piping. You might need one to isolate the pump, but hopefully that's a gate valve wide open so it doesn't cause much head loss. But you don't want to be having like a butterfly valve or something back there because it's going to create a lot of head loss, and that just creates more problems for cavitation. The other thing you look for on cavitation is leaking fittings, because if you're sucking air into that water when it's going up into your pipe, those air bubbles are going to collapse a little bit, and that's going to cause you problems too. So those are just some of the things you might be looking at, okay? Now, if you look on, I got some pump curves, which we'll get to probably Wednesday, but if you look at the one on page 153, you'll see over there on the right how they have NPSH listed for that pump curve. See, what they're doing on page 153 on that pump curve is they're telling you, you know, for whatever condition you're pumping at, here's how much NPSH you need, okay? So this is a number that you do pay a little bit of attention to if you're lifting the water out of a reservoir, is when you'd be thinking about it.
What page is that again?
153. If you look on that pump curve on the lower right-hand side of it, you'll see an NPSH column there.
Okay.
And what that is, that's telling you for these different conditions where you might be pumping at, you need this much energy to pump effect, to have good NPS, to have, for the pump to function properly. Okay, and we'll get to that here in a bit, okay? And I'm pretty sure I posted those links. If you weren't here on Wednesday, have a look at those links. They demonstrate cavitation. They're just little 5-minute YouTube videos. They're worth looking at. I mean, honestly, I mean, when you're out there working, I don't think you're in the office all day calculating all this stuff up. Maybe quite as much as we do, but we want to give you some background in it. But the one thing you want to do is have an understanding. Okay, if my pump sounds like this, it probably means this. And if I sound like I'm pumping rocks, I'm probably cavitating. And if I'm cavitating, well, what am I going to do about that? You got to lower that pump down. You got to watch the fittings on the inlet side. You got to look for air leaks. That's what you got to do. Okay. That's kind of the thinking on that. Okay. And what we're doing here is just running some numbers to kind of show what's going on there. Cavitation's caused by not having enough energy in that water that hits the pump, and that can lead to the water vaporizing, and then those vapor bubbles hit that high pressure area in the volute, and they just collapse in. They kind of implode. They don't explode, they implode. And that can just chew up your pump pretty bad if that happens. So we good with that? Okay. Okay, let's kind of keep going with this if we're all right with that. Let's have a look at page 143. And let's look at power in pumps, because that's really how we size pumps. As we look at the power, it's related to that. Okay, power is a combination of what's called work and time. Okay, work actually has a very specific definition in physics. Okay, what work is a force applied over a distance. So let's say you're a pump, you got to lift 30 pounds of water 20 feet. That would require 30 pounds times 20 feet, and that would be 600 foot-pounds of what's called work, which is pretty much equivalent to energy, all right? So if a pump's lifting 30 pounds of water 20 feet up in the air, you take the force, which is the weight, 30 pounds, and you multiply it by the distance, 20 feet. Now, if you got 5 feet of head loss, if you're pushing that water through a piping system, and you got head loss, you add that to the lift. Because see, the pump doesn't know the difference between lifting water 20 feet and overcoming so many feet of head loss. It doesn't make any difference to a pump, okay? It's resistance is what it is. So if you got 5 feet of head loss, you just add it to the 20 feet of lift and get 25 and multiply that by 30 and get 750 foot-pounds. Okay? So the idea of work is its force, which is weight of the water, times the distance, which is the lift and the head loss. Okay? So we got questions on that? We doing all right? All right, now we actually rate things in horsepower, okay? Power is the ability to do work quickly, okay? All right, so power is a measure of the amount of work that can be done in a given amount of time, all right? We measure it in horsepower, which actually is the power of a horse, okay? And what's going on here is back in the Industrial Revolution, they started inventing steam engines. They started running out of timber in Britain because they were cutting down their oak forest to make ships out of them primarily, and they burned a lot too, and they started running out. So they needed a new source of energy. And luckily, you might say, maybe unluckily for the 10-year-old kids that often did the mine work, they found coal, surface shallow coal, and they send people down into those shallow mines to dig that out. Used it instead of wood to burn, okay? And as we know about Britain, it rains a little bit in Britain, just a bit, eh? Yeah. And so what happens is that water table starts coming up into those mines, and that's a problem, okay? So what they got to do is get that water out. So to do that, they used the engine of their day, which was a draft horse, okay, to get the water out. Okay, now they started inventing steam engines because simultaneous with this, we get this industrial revolution going, right? And they invent a steam engine, and a fellow named James Watt didn't invent it, but he did a lot of the development on it, and he wanted to market his steam engines, okay? Now, horses aren't free, right? You got to give them somewhere to stay at night. You got to feed them. You got to do all this stuff. They cost money, just like anything does. He said, well, I can sell you this steam engine. It'll do the work of this many horses, and it'll do it cheaper. I mean, that's kind of how that all came about. So he rated the steam engine he was trying to sell versus a draft horse, and came up with what's called a horsepower. Okay. So if you got a Corvette, you really do have 350 horses under the hood. That's really how it works. Okay. They're just really fast horses, very fast horses. All right. So what James Watt figured out was that one horse could lift something on the order of 1,000 pounds of water 33 feet in a minute, as dewatering the mines. Okay. All right. So that means 1 horsepower is 33,000 foot-pounds per minute. So it can lift 1,000 pounds of water 33 feet in a minute. And when you multiply that stuff together, you get a horsepower, which is 33,000 foot-pounds per minute. Okay? So that's kind of what's going on with that. Now, of course, we're interested with horsepower as it relates to pumping. So we got to look at the water and kind of its characteristics to figure this up. Okay. Now, horsepower then is a combination of the TDH, which is in feet, the total dynamic head in feet, and the flow rate. If you put those together, you get foot-pounds per minute if you put in some conversion factors. Okay. So I've got this little formula here on page 143, the derivation of it. If you take Q in gallons per minute, convert it into pounds per minute by multiplying it by 8.34 pounds per gallon. Okay, that would get you pounds per minute. And then if you multiply that by the head, the TDH is really what that is. The lift and the head loss added together, you'll get pound-foot per minute. If you then divide that by 33,000, you convert into horsepower. Okay. All right, so we can simplify that as shown below. There's a little bit simpler formula for that, and that is horsepower is flow times head over 3960. The 3960 is a conversion factor that is the combination of 8.34 and 33,000. So here's the formula this is how we'll use it, right there. And that's on your formula sheet. Okay. So that's the basic way we're going to find horsepower. And really, it's if you just have that formula, it's pretty straightforward to do. That formula is on the right-hand side in the lower corner is where it's at. Okay. So that's the basic formula we're going to use to find horsepower. So if we got 300 gallons per minute and a TDH of 140 feet, what's the water horsepower required? Okay, so by water horsepower, I mean the horsepower that's delivered to the water by the pump. Okay, so I'm on page 143 at the bottom. Yeah, I'm not quite sure. Yeah, it comes out pretty good. 10.6? Yeah, okay, 10.6, yeah, okay.
The units will be horsepower?
Yes. And it all kind of comes out magically. You don't really have to worry about so much on the units on this. So what you're going to do, you're going to take the 300 gallons per minute times the TDH of 140 feet, and then you're just going to divide it by 3960, and it all just magically comes out in horsepower. I got 10.61 horsepower. Now I'm going to call that WHP, water horsepower.
Water horsepower and horsepower are synonymous.
Yeah, water horsepower is a type of horsepower. And see, what's going on with a pump here is there's a lot of stuff going on as you kind of go from the motor to the pump to the water. You got efficiency losses every step. So we kind of put a little W for water horsepower, B for brake horsepower, and M for motor horsepower, depending on where we're talking about. But it's all just horsepower. All right. All right, now let's kind of have a look at what I was just talking about there, because we've got some different types of horsepower, and I've got them on page 144. They're terms for them. Now, we just calculated the water horsepower, which is what's delivered to the water. There's also what's called the brake horsepower that comes out of the motor and goes to the pump. And there's also the motor horsepower that goes to the motor. Okay, so we kind of call each one of these things out. Okay, so they're all horsepower, but they occur at different points in the system. Okay, now we have water horsepower, which we just calculated. Brake horsepower comes out of the motor and goes to the pump, and then motor horsepower comes into the motor. Even though the power company, how do they sell their power? What unit do they use? Kilowatts. Yeah, that's another power unit. Okay, they actually sell kilowatt hours, but we'll get to that in a minute. So a horsepower is 0.746 kilowatts. Just two different units for the same thing. All right. And that's on the formula sheet, and I don't know, I've got that somewhere, I think.
It's
Also on page
145.
145, okay, thanks, 145. Okay, now, you might say, well, why does this change? And the reason it changes is we have different efficiencies of these devices. They're mechanical devices. They're not perfectly efficient. So the motor has a certain efficiency, the pump has a certain efficiency, and what that does is cut down on the deliverable power each step of the way. Okay, so efficiency is output over input. Okay? It's what you get out versus what you get in. Efficiency is measured in percent. Those of you in the water program might remember going over this with Brian about a year ago. It's what you get out versus what you put in. It's always 100% or less. Normally it's less than 100%. 100% is perfectly efficient, which there's no machine made that'll do. Yeah, right. That's an impossible dream. It doesn't happen, right? Okay. And nowadays and all this like energy, changing our energy sources and all that, that's one thing they're looking at is efficiency. How efficient is it to store electricity? They talk about using hydrogen as a storage device. How efficient is it to generate hydrogen? They always look at this stuff because it's losses. You have losses of energy, so the lower the efficiency, the more energy you're losing. So what's happening there every step of the way is you're having efficiency losses. Okay. So the brake horsepower is the motor horsepower times the efficiency of the motor. I'm on page 144. And the water horsepower is the brake horsepower times the efficiency of the pump. So the deal on this is every step of the way, we're losing some of our power because those mechanical devices just aren't perfectly efficient. Okay. So if we're delivering 26 motor horsepower to a pump, and if the motor is 86% efficient, and the pump is 74% efficient, how much power is delivered to the water? Okay. So we got 26 horsepower coming in, but that's not what we're going to get coming out. That's going to get knocked down a bit because we have these efficiencies, all right, that we got to deal with. All right. And I think I was mentioning when I bought a furnace a number of years back, you could get a high efficiency furnace, but you had to spend more on it, but you could get higher efficiency. Usually you get more stuff on there to make it efficient. You got to spend more money for it. It's also harder to maintain usually. All right. Y'all getting about 16.55 or thereabouts. So what we're doing, we're just knocking down that 26 horsepower each step of the way. So by the time we get to the water, we're at 16.55.
5%?
That's horsepower, is what that is. Okay. So are we doing all right with that? Okay. So we're just doing this one step at a time here, okay? Now, the thing is, this is if I know what horsepower is coming into my motor, and if I know these efficiencies, I can figure out what's going to the water. But the truth is, usually I go the other direction. Normally, I know what water horsepower I need. I want to back out to get to the motor, okay? So if I've got motor horsepower and I'm going to water horsepower, I multiply by efficiency. But if I'm going the other direction, if I know the water horsepower and I got to back out to get to motor horsepower, I divide by the efficiency.
So is the brake horsepower, is that what we're calling pump efficiency?
The brake horsepower has to do with the brake horsepower. It has to do with pump efficiency, but they're different things. Efficiency is like a ratio. Brake horsepower is an actual power. Okay. So let's say I require 42 water horsepower. I know that this is what my pump's going to need. And I want to know what's going to come into the motor. Okay. What I would do, see now I'm at the water horsepower end. Okay. I'm going to need more horsepower than that coming into the motor because I've got these efficiency losses. So what I would do in this case is I would divide by the efficiencies, and that will get me back to the motor horsepower that's required. Okay. So if I divide that out, I'm going to come up with 61.8 motor horsepower. See, I'm walking it back is what I'm doing. I need 42 horsepower delivered to the water. So what I have to do then is divide the efficiencies out to get to what is coming into the motor. Okay. So what's happening here is I know I need 42 horsepower here. So I'm going to take that 42 horsepower and I'm going to divide it by the efficiencies of the pump and the motor. 0.79 and 0.86. And that's going to get me to 61.8. So I'm going to have 61.8 motor horsepower. And what's happening there is I've got 86% efficiency for the motor and 79% efficiency for the pump. So each step of the way, I'm dropping down a little bit. Okay, but what I'm doing, I'm calculating that way, so I divide the efficiency out. Y'all with me there?
Okay, so to get the required 42 horsepower that you want for the outflow, you're gonna have to have at least 61.8 horsepower going into the system.
Yeah, because it's dropping down each step. Yeah, right. But I'm calculating it the other direction. So I'm
that's just like a minimum, right?
Yeah, right.
It's like when, by the time you get to the shaft, you've lost 14%.
Yeah.
Once it comes out of the loop, you've lost another.
Yeah, right. So you drop it down. Okay, we good? All right. All right. All right, let's let's look, we got a bit of time here, so let's walk through, we've got one on page 146. So let's see if we can put a bunch of this stuff together on page 146. Yeah, we'll jump ahead there. Okay, so we got 300 gallons per minute. And we're going to pump that against 175 feet. Okay. So how much water horsepower would that be?
13, 14.
Yeah. Okay. So what do you do? What's the last thing I got to do to get water horsepower out of that?
Divided by the, 3960.
Yeah, that magic conversion, right? 3960. And that'll get me water horsepower. And that's 13.26. Okay. All right. Now, I want to figure out what size electric motor that I need. Now what that is, that's how much power is coming out of the motor. So if I got 13.26 water horsepower that I need at the pump, or excuse me, delivered to the water, what do I do to get the energy coming into, or the power coming into the pump? Yeah, 85%. You with me there? 15.6. So this is how big the motor has to be. The motor's got to output at least 15.6 horsepower. Okay. You okay with that? So if I got an 85% efficient pump, I got to deliver 15.6 horsepower to the inlet on that pump, so I get what I need, which is 13.26 out. Okay. All right. Now, how much horsepower do I deliver to the motor? Yeah, 17.33, because I got a 90% efficient motor. Okay, we good? And that's going to be 17.33 motor horsepower. So that's what I got to deliver to the motor. We good with that? Okay. Now, how many kilowatts is that? 15. I got something lower. There's a conversion for kilowatts?
Yeah, 12.92.
Yeah, there we go. Okay. So I got 17.33 horsepower. That's coming into the motor. All right. And I know that I've got 0.746 kilowatts per horsepower. So what that's going to get me then is 12.93 kilowatts. So that's the power in metric units. That's how the power company wants to sell it. That's how they measure it. Okay. Y'all good with that? That's just a unit conversion to get it into the power company. If you look at your power bill, they sell power in kilowatts, is what they do. Okay. So then the last little bit on this, because actually if you look at your power bill, they sell you kilowatt hours. Okay. So we're going to run this thing 9 hours a day. That gets me into the kilowatt hours per day. If you look at your power bill, that's how it's sold, kilowatt hours. Okay, so 12.93 kilowatts times 9 hours a day times 12 cents a kilowatt hour.
Does the days get
No, it's, this is gonna be per day is how it's gonna end up being. And if I multiply that by 12 cents, what I'm gonna come up with is how much it costs me for power-wise to run this pump every day. $13.96, okay? So that's how you back out. See, we started here. Here's what I gotta do. But if we know these efficiencies and we know the cost of power, we can figure out what it's gonna cost, okay? Y'all all right with that?
Yeah, just depending on the direction we're going is if we multiply or divide, right?
Yeah, and think whether you want the number to get bigger or smaller. If it's gonna get bigger, which normally that's how we do it, we walk it back, divide the efficiency out, and that will make it bigger. Okay.
That makes sense.
All right. So that's the basic numbers that you run if you're gonna analyze your pump system. So we good with that? Okay. Now, how about, why don't I get you that homework back, and why don't you just finish it up, because there's a couple other things to do with it, so, why don't I just hand it right back to you, so you got it. And let's do some of this stuff, just so we get that figured out. So, how about for Wednesday, and what I'll try and do, I'll get this back to you Thursday. Y'all gonna have class with Brian on Thursday?
Yep. Yeah.
Okay, now remind me to do this, okay, and I'll get it right back to you Thursday so you have it, because I know that some of you aren't here on Friday. So let's finish this stuff up. So you've already done 14.1, so that should be done, but let's do 14.2, 3, and 4. Those are just some little short questions on efficiency and power and such. And let's finish 14, 5, and 6. Okay? And see if you can get those knocked out for Wednesday. Okay? 2, 3, and 4 are all pretty quick little problems. They're just like what we were doing up here, these unit conversions. And then see if you can finish 14. And let's make that due Wednesday
So 5 and 6, we're just trying to find the TH, right?
for today. But now we're going to go finish them up. So do the whole 9 yards with them, with the power and the MPSH and all that. All right. All right, if, last thing too, if that midterm didn't go well to you, I'll have a makeup down there in Red Cedar Hall 111, if that's a concern to anybody, okay? I'll have something there. Yeah, we're done, sorry for all